So when we look at the current homework for Chapter 1 and Chapter 3, for Chapter 1, they're fairly quick, immediate definition answers. Having you go through the process of writing it down does help you remember things. So the more you write and think and read and do all of these different learning techniques, the more likely you are to remember it. Some people are just lazier than others, and that would be me. I wouldn't write any of those answers down. I'd look them up and be like, oh yeah, that's what it is. That makes sense, and move on. Okay? So because of that, it's very hard for me to actually assign homework questions for me to be able to grade, at least so far this semester. So both Chapter 1 and Chapter 3, for the most part, are just kind of practice. So what I went through for Chapter 1 is I actually looked at a couple questions. So scientific method questions, 5 and 7, and then just trying to mess with your head, questions 13 and 19. So if we look through Chapter 1, as far as the questions that you see, they are, for the most part, just kind of look things up and get you attempting to be interested in the material. So easing you slowly into chemistry by not asking any questions about chemistry. Okay? Chapter 3 then goes through and starts to introduce physical states, and a lot of that is just definitions. Okay? As we already started to talk about, a lot of those questions also push back to the periodic table and say, oh, what's the symbol for iridium? Okay, well, if you don't know what the symbol for iridium is, you can open up your textbook, and it should be in the cover, and I think in all editions. Yes. It gives you the name and the symbol, so you can flip through that to try and find what the name and the symbol is for that compound. But again, if I asked for the symbol for iridium, you look it up, and you tell me that the answer is IR. Okay? Writing that down, how useful is that going to be? Probably not very useful, okay? Particularly as far as me going through and grading it. Okay. So the homework are all at the end of the chapter? Yep. So here you go. Yeah. So that's going to be one of the other issues. When I went through and looked at these, that came from the 6th edition. When I got home, I was hoping to go through and look at the 7th edition to make sure the names matched. I didn't have time to do that yet. Okay. So that is one of the reasons why I'm listing the topic for the questions. Okay? So that ignore the number, focus on the topic. I want questions based on the scientific method. So what you can go through and do is look at your textbook. Does it have questions based on scientific method? So worst case, you read all the questions. Okay, oh, there's something that says something about scientific method.
Is the evolution of chemistry?
Check every single question. Is there a question in there that asks about the scientific method?
It is 5 and 7.
Okay, so if you go and take a look, what question numbers were those? 5 and 7. Okay, so the two questions I asked did happen to match up between the editions. So what you want to do is look for these topics of questions. Those topics are more important than the numbers, because if you're using a different textbook, I have to be able to help those students as well. Okay, does that make sense? So look for the topics, not the numbers so much. Okay, I will try and be better about making sure they're all in chapters or in edition 7, but it's just going to kind of come with whatever I have most available and what time I've got to build it. Okay, so with Chapter 3, I went through and looked at all of the individual categories and wrote all those categories down. Again, a lot of the questions that show up in here are definition questions. So you'd end up writing down the definition. To me, I don't personally find that useful, and usually most students get frustrated when those questions get assigned because it's busy work. All you're doing is photocopying a textbook. Okay? If you're a person that needs to be able to write to actually learn, go ahead and write it out. Okay? It's not going to hurt. Okay? You will be seeing questions where I will have something to grade. That's when we move back into the PSS chapter, if you will, in Chapter 7, or in Edition 7, or in Chapter 2. Okay? Both of those will have questions that require actually writing something out, so some calculations. Okay? So if we kind of go back to Chapter 1, we want to come up with an idea on what we're looking at. Okay, so chapter 1 kind of goes through these grand ideas of what science is, what chemistry is, and all of these fun things. Okay, so we can look at a strawberry pie. So let's say I brought in a strawberry pie. Okay, and we could go through and think, well, why did you bring in a strawberry pie? And a pessimist might look at it and say, because he's a mean, evil person, and he's going to eat strawberry pie in front of me, and that's just rude to do in the morning. So I really like strawberries. Okay? An optimist might say, oh, he's going to share that strawberry pie with everybody. Okay? What does a scientist do? Scientist looks at it and says, I can make that pie better. Okay? So the scientist is going to take a look at whatever we're studying and try and figure out what made it up. Okay? What are the individual pieces that go into that? How can I improve on the overall system or the overall topic? Okay? That's kind of the goal behind what science is. Always build. Okay, so let's think about that. What are the indivisible parts of this pie? So let's now think we're scientists and we're going to try and build this pie. If we had anybody in here make, let's start with a pie first. Okay, pie crust. We've got some people that know how to make pie crust, so we could start listing off our individual pieces. What else would need to go into this pie? Okay, we got strawberries. I know where you're going with that. I don't want to get there yet. I just realized blue is an awful color, for this room at least. We've got the pie crust. We've got strawberries. I think I heard that, a glaze. So we could look at our larger aspects of this. We've got these 3 primary groups. Okay, so we could look at it from one perspective as a scientist. We could say, well, I can build that. I'm just going to go to the store, buy a pie crust, strawberries, and a glaze, and I'm going to mix them all together, and I'm going to have a fantastic pie. Okay, ooh, good call on that. Okay, so the first person that went through, I can't spell tin. Let's try that again. Okay, first person that went through and tried to build this didn't have a pie tin, and they threw it all together, and it just turned into a goopy mess. Now that we put in a pie tin, now it's actually holding together. Okay, and we now have a pie. Okay, I make a really good pie. What are the odds that my really good pie is going to match up with some store-bought, no offense, junk? Okay, probably not. I'm probably still going to win that argument. Okay, so what can you do? We can now go back through and say, okay, I do have these individual pieces, but can I make them on my own? Can I put better ingredients into each of these things? So how do we make a pie crust?
Butter.
Okay, actually, I don't know the answers to this one, so you might have to help me. Butter.
Flour.
Sugar. Flour. Did I spell flour right? I think that's right. Salt.
Baking powder.
Okay, we might get a baking powder. Somebody else? Whoops. Powder. Eggs go into a crust? Okay, so we get some variations here. This makes it even more interesting. I wouldn't have put eggs in a crust. Okay. So depending on different recipes, you might generate different ingredients to make these. Somebody else brought up an important ingredient, if you will, that wasn't listed on here. Said, oh man, come on, stop it. Running out of space. Yeast is a new one to me too. I wouldn't have put that in there either. Okay. So let's say we took all these and we smashed them all together. Do we now have a pie crust? We need heat. Okay. So there's yet another piece that needs to go into this. We need to somehow mix all of these in the proper proportions and then add heat to kind of cook it and bring it together. Okay. And we would still have to do it in the tin. Okay. So we could go out and purchase each of these things from the store. Okay. But what type of butter do we get? There's salted, there's unsalted. We could even do fake butter versus real butter. We could go to a farm and get the absolute best straight from the cow butter. Okay? Are those additions going to make a difference in the overall pie? Okay, everybody say yes? Okay, a few people are saying no. Why would you say yes and no? There's a threshold. Okay, everything we do in science has a threshold. And we decide within that individual experiment it's not going to matter. So if we take a look at the varieties of butter, Okay? How many of you can taste a difference between salted and unsalted? Okay? I think I can too. Okay, but maybe you can't. So a few people raised their hand yes, a lot of other people didn't. So for those of you that can't taste a difference between it, is it going to matter what butter we use? No. So what's our threshold that we're evaluating when we try and put together this pie? Our own personal taste. Okay? Some people's tasting abilities are a lot more accurate than others. Okay, so butter was a reasonable example. Are there different forms of sugar? Yeah, you could go with white sugar, brown sugar, powdered sugar, turbinado. Anyone heard of that one? Yeah, what's going on with that? Okay, it's a different processing. When we look at white sugar, they tend to process that to get it white. But we can not process it as much and get a lot better, or depending on your opinion, better flavors out of the sugar. Okay, we could use different sweeteners. So these are all different aspects that end up coming into this. So what we're trying to do is break apart this pie into the individual pieces to make the best that we can. And then we ultimately have to go in with our overall assumptions from the beginning and say, okay, what things are we basing this off of? What's our threshold behind this? Okay? And we'll look at those thresholds and go back and measure things more. Okay? So a lot of what science does is takes an individual species and says, okay, how do I break this apart into smaller things? Okay? So that I can put it back together again. Okay? Which is also what an engineer typically does. Okay? Depending on your skills, like mine, you tear it apart and then you forget how you put it back together. And you just got a bunch of parts lying around. Okay? So our goal behind science is to always take everything apart to figure out what those indivisible pieces are so that we can then put it back together. Okay? And we want to come up with very strict rules on how we go through and do this. Okay? Why do we want strict rules on it? So it comes out the same every single time. Okay? So now let's say you go through, you made a better pie than me. Now you're going to go out into the market and compete against me. Okay? Well, I can make 60 pies, you can only make 2. I'm going to win. Okay? Because I can get my pies out to more people and sell more than you can. Okay? So you need to be able to scale your project up, scale that reaction, and allow other people to do it as well. Okay? So we have to have some consistency across the field. And these recipes, if you will, need to get listed out for everybody to have access to. And that's what science is trying to do. We generate these standard rules so that when we go through and tear apart a pie, everybody tears it apart into the same pieces, and we know how to put it back together. Okay? So, what we're ultimately trying to do is learn something new. Okay? And a lot of the scientific method comes back to us. It's just learning. Okay? We don't care what we're learning, we're just trying to learn. Okay? So, if we start off the scientific method, and you'll notice, for those of you that have checked or read the text, my method is slightly different than what the text has. Typically, when I say we start science off, we make an observation. Okay? Lead is cheap and abundant. Gold is expensive, okay, and limited. So what do I want to do? I want to turn lead into gold so I can take some cheap material and make it an expensive material. So we're trying to take advantage of those simple observations and try and build it. Okay? So once we've got that observation, we then want to come up with some kind of hypothesis. Okay? If things are all made up of the same materials, then I should be able to build outwards from this. Okay? So we can go through with a hypothesis. Okay? And we're going to come up with some kind of statement that summarizes what we're trying to do, okay, or what we hope to see. Okay? Once we know what we're actually trying to do, then we're going to have to design an experiment. Okay? So we go through and say, okay, we're going to take lead into gold and we're going to put it in a beaker and we're just going to stare and watch it, okay, and see what happens. Okay, so we do that experiment. Cool. How many people have stared at lead and watched it turn into gold? Okay, you probably haven't done that. How many of you would expect that if we did that experiment, what would you expect as the result? Took a block of lead, put it in front of each of you. What are the odds it's going to turn into gold? Not going to happen. So what does that mean? And this is everybody's least favorite word, particularly when it comes to education. Failure. Okay? 90% of science is failure. Okay? For various reasons. In most cases, it's because the experiment that we designed from our hypothesis wasn't very good. It didn't take into consideration all the important variables. Okay? So maybe we need a different type of beaker. Maybe we need a smaller amount of lead. So we go through and we start adjusting the individual variables that we have control over and design a new experiment, okay, with a new hypothesis. And we try again. What happens the second time? 9 times out of 10, failure. Okay? So like I said, a lot of my colleagues hate the word failure. In fact, most students hate the word failure too. Okay? But it's not a bad thing. Okay? Failure just means it didn't work. That just means the initial hypothesis was wrong, which means we've now limited the number of experiments that we can do. We removed one of the possible options. So we try again, and again, and again, and again. So you look at PhDs. Everybody thinks a PhD is this big, important, special person. You go back and look at what they've written across 5 years. Most students, when you get up to that level and you start to become a PhD and you go through the research and you want to see what somebody else did, you go back and look at their work and they're like, that's 2 weeks worth of work. Why did they spend 6 years doing it? Okay? It's really easy once you know the answer. If you don't know the answer, it's a lot of going back and forth until you can start to build up what pieces of information are missing, what are the individual variables, and start building your experiment appropriately. Okay? So that's one of the things that I want to try to strongly encourage you guys to avoid being panicked about. Failure is an okay thing. Okay? In most cases, it's actually a good thing. It's only in that 1 or 2 case when it comes at the end of the semester that failure becomes a bad thing. Okay? But through the rest of the semester, I want you guys to consider failure as a good thing. Okay? As long as you then move back and try again. It's all about that repetition and repeating those individual experiments, repeating the calculations, repeating how you approach the problem. Shift your focus and try again. Okay? Yes, it's going to feel like you're just hitting your head against the wall 9 times out of 10. But that one time, it's one of the most amazing rushes and feelings that you can possibly get. Okay? So you go through and talk to research scientists. They're the exact same thing. The only reason they're going through and continually failing is for that 10% of the time, that 1 time out of 10 that something worked. And now all of a sudden, they've created something amazing. Okay? So it can be rough, but it's worth it. Okay? There are scientists that are actually addicted to being scientists, okay, for that particular rush. So let's say now that we actually went through and did this failure a whole bunch of times and we've actually succeeded. Okay, we end up with 2 possible results coming out of this. We end up with a scientific theory. So we've come up with some way to explain what we're doing, but we don't have a way to directly measure it. Okay? Or we come up with a natural law. We get a direct measurement coming out of it. So we can look at heat flow, for example. Okay? We'll always get hot flowing to cold. We'll never get cold flowing into hot. Okay? That is a direct observable within an individual experiment. So we end up generating a natural law. One of the fun things with natural laws is because they're so cut and dry, we're starting to run out of those opportunities. Remember, this has been 800 years of science. Okay? There's not a whole lot of natural laws left. Okay? You might even run the assumption that they aren't left. Okay? Really, to push into those natural laws, you're looking at driving into hardcore theoretical physics. As cool as that may be, I know I'm bad at math and I probably won't adjust that. Okay? My failure rate there is probably closer to the 99%. Okay? Other than that, we end up with scientific theories. Okay? We have explanations on what's occurring, and we've generated enough data to support that that conclusion makes sense And when somebody else goes through and does the experiment, they get the exact same results. Okay? So science is something that's not done by one person, but by hundreds of thousands, if not millions of people. Okay? And not just done within a year, but done over a large expanse of time. Okay? Which can be very frustrating because you could go through based on the assumption that somebody did something right. Okay? Oh, they published this work. That means they were right. And then you go into the lab room and you try and repeat their experiment and it fails. Okay? The first assumption is that you screwed up. So you do it again and again and again. You keep getting the same wrong result. So finally you come back and you challenge them. You say, you know what? Your experiment didn't work. Okay? I don't know what you did, but it's not working. That then brings up arguments against it, and then we start to spread out into other research groups, and we try and figure out what happened. In some cases, particularly in the high-pressure environment that we're running into with science now, you will find that some people are actually fudging data, okay, to put it politely. Okay? The ultimate sin as far as science goes. Okay? And a lot of that is coming back to, I came up with a hypothesis, I'm going to design an experiment to prove that my hypothesis is right. That is not how science is done. Okay? And the reason why people are doing that is they don't like the failure. Okay? Failure is an inherent process in science. We need failure to be able to learn and push forwards. Okay? So the one big extra thing that I added in here was that failure loop. Okay? Because, like I said, nobody likes talking about failure, so your textbook didn't address it either. What the heck? So now what we want to do is take a look at chemistry's role in our science field. Okay? So we've got mathematics and physics, typically on one end of the spectrum, and then we have biologists, and you can see how well I know the other half of the field and other stuff. Okay? Chemistry bridges the gap between that hardcore theoretical understanding and bridges it into the real world. Okay? Since I know this works, I'll add in one more thing that we could add in here. Sorry if this offends anybody. Okay? Engineers, I would typically classify on that real world aspect. Not necessarily a bad thing, but I like a little bit more theoretical stuff. Okay? So the chemist's role is to kind of tie together those theoretical rules and allow other people to then interpret and manipulate those rules into real-world applications. Okay? That doesn't mean chemists don't do either end of the spectrum. Okay? You will see chemists that are strictly application-based. Everything that they do to research has some end goal result, okay? And one that is financially feasible. Then there's other chemists that work solely on theoretical stuff because they figure if we build up enough knowledge on one end of the bridge, we can start to find some way to apply it across. Okay? So chemists have this kind of massive role in between. So we end up with a bunch of different branches that come out of chemistry. You get organic chemistry, my personal favorite, so of course I'm going to list that first. Biochemistry, which is actually kind of low on the totem pole in my opinion, but apparently I'm teaching it next semester. Maybe I shouldn't have recorded that. Biochemistry, which then takes in biological sciences and goes back to the individual bonds that are breaking and making within each of those systems. Okay? Then you can get inorganic chemistry. Some people like to classify both this class and your 151 sequence as inorganic chemistry. I think that's a misnomer. The class that you're in is supposed to summarize all chemistry. Okay? So you're looking at both or all of these fields. Inorganic chemistry zeroes in primarily at the transition metals or the transition elements and looks at their individual chemistries. Okay? So what are some important advances in inorganic chemistry? Pretty much everything I'm holding in my hand is due to inorganic chemistry. Okay? You're looking at non-organic materials, so non-carbon containing compounds that then we've designed and built to manipulate other physical elements, okay? Electrons. The very last thing that we get is physical chemistry, And again, each of these branches can further subdivide into theoretical and application-based. Physical chemistry, in most cases, tends to apply largely back strictly to physics, but we tend to spin it a little bit more and look more at things that are a little bit larger, some atoms, some molecules, that kind of stuff. Okay? Questions about any of that? Okay. Pretty sure that is chapter 1. Okay? Anybody go through and read chapter 1 already? No one wanted to volunteer. Okay. So what I would recommend, just so you guys know, I should have mentioned this on Tuesday, as far as study habits go, how you should be studying is reading the textbook before I talk about it. Okay? After the fact, it's not necessarily a bad thing to read it, but after the fact, you should really be working problems, trying to learn and hone your skills with the material. Reading it after the fact just kind of slows you down. Okay? That said, I've never read the textbook ahead of a lecture, but it is a good thing to do. Okay? Remember, I failed organic the first time. Okay? You don't want to be in the exact same boat I am. You want to be in a boat that's floating above me. Okay? Okay? I'm kind of underwater a little bit. So, what we're now going to do is move into chapter 3. Okay? And chapter 3 is going to look now at matter. Okay? What makes up matter? Why are we looking at chemistry in general? The reason we jump to this chapter as opposed to going into chapter 2, or even that PSS section in edition 7, is because if we jump immediately into those earlier chapters, that's where we start dealing with numbers and math, and that just gets confusing. Okay, so what we want to do is step back. We've looked at kind of the planet. Now we're going to look at the forest, okay, and see what things kind of develop chemistry. What are we looking at? And so really there's two main branches when we evaluate any chemical reaction. We can get a qualitative reaction and a quantitative response. Anybody know what either of those two terms means?
Qualitative is like the makeup of it, whereas quantitative is more of the amount, the number.
Okay. Quantitative, typically we assign a number to. It's a mathematical representation. Okay. How much was made? Okay. How much was removed from the system? Qualitative looks at big things. Okay. Color and explosion. Okay. Gas being evolved. So we're looking at larger, broader terms. If we're going to look at how chemistry was first determined and discovered, which of these two do you think was probably the first process? Qualitative. They're easier things to observe. We can see them with our naked eye. We don't have to bust out a ruler. We don't have to have a balance. We don't have to be accurate at anything. Okay? We just have to say what's going on. Okay? So the qualitative relationships are a little bit easier to understand, which is why we'll go through those first. Okay? So we need to come up with some place to start. So if we go all the way back 800 years, okay, and we want to figure out how they started to develop science. Okay? So we want to know what our individual compositions are. Okay? If you go back to chapter 1, for those of you who read it, you get fire, water, earth, all that fun stuff. Okay? I want to take a step further down the food chain as far as that thought goes and see if we can see something else. What is 70 to 80% of the composition of life? Water. Okay? Water shows up pretty much everywhere on our planet. Okay? Does it always show up as the same thing? No. We end up seeing different forms of water. Okay? This was an attempt to show these different forms. It kind of worked. On the far left, what do we have? We could call that snow, okay, but I was preferring something else. Ice. And then even better, I heard it even, we're looking at a solid. Simple, simple observation. So think back to prehistoric persons, taking a look at this weird white fluffy stuff floating down from the sky that had some kind of solid characteristic, particularly when they shoved it all together and threw it at somebody's head. Okay? Okay, so it has a particular characteristic associated with it. Okay? What happened to that solid, okay, when the weather warmed up? It melted. Okay, and it became liquid, okay, or what we typically know as water. Okay, why would that be important? How did we get that liquid water? Where did it come from? Maybe go back to heat, or just it came from this solid. Okay, why is that a kind of odd observation? So if we go back to life, everything needs liquid water, okay, or some form of liquid. We drink it. We have to stay hydrated. If we don't drink water, eventually what happens? We get dehydrated and we die. Okay? So if we go all the way back to the beginning, we say, hey, liquid water is really, really, really important. Okay? And it has these particular characteristics. It fills the volume that contains it. Yeah. Okay? It's kind of amorphous. It has some kind of shape to it. And if we think back and say, okay, well, where did this water come from? We now have two things. We've got a solid and a liquid, both very different characteristics. So our initial assessment might be that they're different things. They are not related. Okay, so there's our first hypothesis. So then we go into experiment. Temperature heats up. What happens to the solid? Melts and becomes a liquid, and now it's that exact same species that we said was different. Now we've got a problem. Okay? We said they were different things. So if we ate the solid, that shouldn't be able to hydrate us. We shouldn't be able to survive with that species. Turns out we can. So what does that mean? Okay. They're similar, or they're the same species with different physical properties. So we start to come up with these lists of what these properties may be, and we know that they are related to each other by a temperature change. Okay? If we push it even further, okay, what happens when we then boil it? We add even more heat to that water. It turns into a gas, so we end up with our gas state. I heard a lot of people saying vapor. Vapor is a common way for gas as well. Okay? And again, we'd say, well, now that thing fills the entire volume. Okay? We don't even see it anymore when it turns into a gas, in most cases. Okay? So now that must be completely different. Okay? But if we go back even further, or not back, but come back into, say, the 1920s, okay, during the Prohibition era, we had a lot of moonshine states, which means they had to go through and distill. What were they doing in a distillation process? Okay, how were they making alcohol? Okay, they fermented it, but that fermentation, for those of you that know anything about fermentation, yeast can only ferment so high. Okay, usually about 15% alcohol is the highest that you can get when fermenting something. Okay, after that point, the alcohol is toxic. It's toxic to us too, for anybody that cares. And it kills the yeast. So how do we get, say, spirits or moonshine or anything with higher alcohol? We have to distill. So what ends up happening in the distillation process? We heat it up and it turns into a gas. We collect that gas and cool it down somewhere else. So again, we now have this third kind of piece of matter. Okay? It is again related to the first two, all through energy, and it's all ultimately the same thing. Okay? So we could start to come up with different ways to separate these and apply these different rules. Yes?
I was wondering, is that how you change salt or water into
So if we want to figure out ways that we can survive, say, potentially on the ocean, if we don't have fresh water, okay? If we drink salt water in the ocean, what happens? Ultimately, you get crazily dehydrated really fast, and you die even faster. Okay? Not a particularly good thing to do. So the problem with that is not so much the water, but the salt within the water. Okay? So now we actually have a mixture of two things. We need water to live, but too much salt, and we end up dying. So how can we separate those two? Okay? What do we know about salt? General, just table salt. Okay? It's a solid. Okay? And its melting and boiling processes, okay, are at a different temperature range than, say, water. So what we can do is now add heat to that solution. What happens to the water? boils, turns into a gas. What happens to the salt? Stays the same. So if you've ever left a pot of boiling water because you're making pasta or something like that on the stove, okay, it usually ruins your pot because you probably aren't cooking with deionized water, and the salt particles then get collected at the bottom of the pot, and you've now ruined an expensive pot. Not that I've ever done that on multiple occasions. So we need to be aware of these individual processes. So what we're going to do is take advantage of those different interactions and try and build different steps. Okay? So we can already now use ways to survive on the ocean, as long as we can build a fire and not burn down our boat, okay? And collect the vapors that come off of it. Okay? So other things that we want to address with this would be what's happening in each of these transitions. How can I move from one to the other? Okay, we've already suggested one of those. What do we have to add to go from, say, the solid, I can do it this way, to the liquid? We need to add heat. We'll come back to that. Okay. What if I wanted to go from the liquid to the solid? So we could add cold, okay, which isn't the easiest thing to do. But how can we relate cold back to heat? We can remove heat. Okay? So we can start to now come up with hypotheses. If we adjust the temperature, we can force these transitions to occur. Okay? And whoever said the pressure one, we'll get to that in a little bit. Okay? So we could now say we're going to transition from a solid to a liquid. Okay? That transition is going to require some amount of heat. Okay? In the case of water, or yeah, I'm just going to have to call it water. Okay? That required X amount of heat. What happens when we move to salt? Did it require the same amount of heat? No, it was different. Okay? So if we're going to try and discuss this transition, we want to come up with something other than just referring to that heat. Okay? So we want to come up with a name for this. What is the transition referred to when we go from solid to liquid? Okay, it is a phase transition. So what we've specified in each of these cases are our phases. What is the phase transition from solid to liquid? It's the melting. Okay, it doesn't always have to be difficult. So we could look at it as a melting point. The point at which we've added enough heat to cause the solid to transition to the liquid. Okay? What about the reverse? We could look at the freezing point.
Can't really see that.
Oh man, this projector stinks. Let's try orange. Can you at least see that it's a different color? Okay. We've got our freezing point. Okay? And unfortunately, you will see other names being associated with each of these. Okay, what happens when we move from the liquid to the gas? Okay, we're looking at the boiling point, or the, and by or I mean the reverse. We can look at our condensation. When we take a look at liquid water, do we ever see the solid to gas transition? Has anybody seen that transition? Right. So, way to predict. Okay. If we look at the solid to gas transition for water, we would assume, hey, that does not occur. Okay, because we don't physically see that until someone suggests dry ice. What happens with dry ice? It doesn't, or we don't see it melt. It goes directly from a solid to a gas. So we can get a solid to gas transition. Okay? We just don't happen to see it with water. So one of our initial hypotheses was that we had to move through these transitions. That's not always the case. We can skip the transitions by jumping across the middle there. Okay? Anybody know what the transition is going from a solid to a gas? Good, sublimation. Or we could look at it as the sublimation points. I've been calling that. How about gas to solid?
Deposition.
Oh, nice. I actually didn't know that one, so I'm glad you answered. Okay. Why might I not know the gas to solid transition? What's that?
Doesn't happen very often.
Well, we don't see it very often. Okay. So if we don't work with it, we don't tend to remember it. Okay. So we now have all of these potential transitions. Okay. Well, why do we not see water or solid, let's go with ice, go into the vapor? Why do we not see that transition, but we do see it for CO2? Okay, is there something else that controls these phase transitions? Is it just heat? Okay, let's pick a more common phase transition that hopefully more of you have seen. Let's look at the liquid to gas transition. Okay, anybody gone up to, say, Denver, up to Mile High City, someplace really high? Only 2 or 3? Okay, that doesn't help. So here, answer my question. You tried to cook both here and up there. Yes? No? Okay. Do you get the same cooking times? No. What changes? You have to cook longer typically. Why do you have to cook longer or differently? The oxygen typically isn't what's happening when you're looking at cooking. Most cooking processes are about controlled removal of water. Okay? So a few people have mentioned what big change occurs as we move from, say, Arizona relatively at sea level up into the higher altitudes. We do look at a change in oxygen, but again, that's not necessarily what's affecting it. Pressure is what's affecting it. What is pressure? Okay? Pressure is the action of physically holding something together. If we take a block of ice, okay, what volume does it occupy? Say it's an ice about that big. What's the volume it occupies?
That size.
There you go. I like that answer. That size. What happens when I take that volume of ice and I melt it? Okay. Say I'm still holding on to it here. I take that volume of ice and it melts as I'm holding it up here. It falls away from my hand. I can't hold liquid water. Come on, right? If I'm going to hold it up, it's just going to fall away. It's going to occupy whatever volume of the container is that is holding it, okay, up to a certain point. What happens when that liquid water transitions into a gas? Okay, it completely dissipates. Why, in one case, is it holding in a physical location? In another case, it's being spread all over the place. Okay, what happens when we add heat? What's happening to each of those individual molecules? They're moving more. The more heat we provide, the more energy they get, the more they move, and the more space they can now occupy because they have enough energy to move out into those areas. Okay? So heat allows us to kind of break those interactions. What happens with pressure? Pressure is doing a very similar process. Pressure is now physically holding it in that one spot. Now, you all have the pressure to stay in this room right now. Okay? Because in theory, I'd yell at you, which wouldn't be the case. Okay? So pressure is also going to hold things into each of these individual phases. Okay? So it's something else we would have to consider when trying to look at our individual experiments. Okay? How would we discover that pressure was important? Well, we'd run the experiment at sea level, and then somebody across the world or in Denver runs the same experiment and says your results stink. Okay? And we'd have to come up with an explanation for why those results don't match, and that's where we could bring in pressure. Okay? Kind of makes sense on how we slowly build upwards based on the information we've got. Okay? So we've got these three primary phases to work with. And depending on what we're dealing with, we're going to be looking at these in different phases, okay, or different species. Most things that we deal with are solids. okay, or at least that we see every day, and that's why I can walk up here and not fall through into the center of the earth. Okay? So what we're looking at is now matter. So we're going to say matter is composed of these three phases, and there's different forms that these phases could then take. Okay? We could mix phases with each other, okay? Or we could have pure substances. Okay? Depending on how we evaluate these or branch these out, we're going to get slightly different interactions, and we would expect different properties to show up. Okay? So if we take a look at matter, we really get two primary divisions: a pure substance and a mixture. Okay? In the case of a pure substance, it doesn't matter where you go, you're going to get the exact same properties. Nothing changes. Okay? A mixture, however, could have different properties. Okay? In different species or different parts of it. So a lot of that is going to depend on what you're working with within each of those divisions. Okay? Mixtures get further subcategorized into two separate sections: heterogeneous mixtures and homogeneous mixtures. Okay? What do those two terms mean? Okay? Ultimately different and the same. So we are looking at different and same. What does that mean? Typically, to get a heterogeneous mixture, what we're doing is mixing multiple phases. Okay, so if I take a liquid and a solid, what's a good liquid to work with? Water. Okay, let's mix that with a good solid. Pick a solid. Okay, so we got a couple different answers floating out here. I'm going to pick salt to start with, because dirt is way too complicated to deal with, but it is a fair assessment. Okay, what happens when we add salt to that water? What's that?
It becomes hypertonic.
Okay, bigger word than I can deal with. Let's do a different one.
It's salty.
It gets salty. What happens to the physical phase of the solid salt and the liquid water? They completely mix. What happens to now the overall phase? Do we have a solid and a liquid anymore? No. Okay. We have one phase. What kind of solution are we or mixture are we looking at? So heterogeneous was different phases. Homogeneous is the same phase. What kind of mixture do we have? We have a homogeneous mixture. Salt water classifies as homogeneous because they evenly mix and they're consistent all the way through. Okay? How is it different from, say, the pure substance category? Okay? Well, if I say mix some salt here, so we give everybody the same amount of salt, same amount of water. Okay? You think everybody's going to mix it the exact same? No, we'll get variations in the amount of salt that someone added to it. Okay? I would guess that at least a few of you here would just stare blankly at it and say, I'm not going to do that. That's stupid. Okay? Fair enough. If I now, being super excited, take all of my salt and dump it into my water, we get both solutions that look exactly the same. Do they have the same properties?
No.
We'll go back to your example. One of them was hypertonic, and the other one is hypotonic. Okay, there we go. Learn something new every day. Okay, hyper being the salt one, and hypo being the clean one, okay, or the unmixed one. Those different properties change. Okay, so we're not looking at a pure substance now. We're looking at a homogeneous solution, and each of those solutions have different characteristics, even though they're both made by the same compositions or the same types of things went into it. Okay? How can we get a heterogeneous system? So let's go kind of back to the dirt, but I'm going to simplify it. I'm going to turn the dirt into sand. What happens when we add water and sand? Try and mix those just like we would our salt water. They don't mix. So what phase was our sand in? What phase was our sand in? You're jumping ahead. Solid. And the phase for our water? Liquid. We now have a mixture that has both a liquid and a solid in it. What kind of mixture do we have? we're looking at a heterogeneous mixture. Okay? So probably, and of course you can always find more difficult ways to go through and come up with different examples. Excuse me. Primarily when we're looking for heterogeneous mixtures, we're looking for differences in phases. Okay? So let's pick another example. Let's say oil. What phase is oil? Liquid. And let's take water. Liquid. We mix those two. What happens? They separate. Okay? We don't get an even mixture. Okay? So what would we classify that as? Heterogeneous or homogeneous? Hetero. Why hetero? Because they're both liquids. Those are the same phases. They aren't mixing. Okay? So we can see things beyond just a standard phase, but those phases now must completely interact with each other. If they completely separate from each other, we're looking at a heterogeneous mixture. Okay, so we could throw in our oil and water thing there. Any questions on that? Is it 9:40? 9:50? 9:40. Okay. Still 30 minutes, don't worry. Nobody turned and looked, huh? Okay. You must be liking what I'm saying then, apparently. It's only like 10 minutes. Okay, so let's shift back to our pure substances. Okay? If we look at our pure substances, we can further subcategorize these. Okay? When we look at a pure substance, we can divide these into compounds or elements, and elements. They are different from a homogeneous mixture, because in the homogeneous mixture, you can separate these through a physical process. So if we were going to separate salt from water, how would we separate those two? Heat. Okay, we could add heat, and what's the heat going to do? Cause the water to turn into a gas, and we can now separate the water from the salt. Nice, easy separation. When we go through and look at pure substances, we don't get easy physical separations. Okay? What we'd have to do is chemically separate these things. Okay? And we are going to address the difference between chemical and physical probably on Monday, because I don't think I'm going to get into it. Okay? So what's happening with a compound versus an element? What's a good compound? Any compound you want. Salt. Okay, and now the harder question, what is salt made of? And don't go all fancy on me. Keep it simple. Sodium chloride. For those of you salt nuts out there, yes, there are other things that go into table salt. Okay, let's stick with the easy one, sodium chloride. Okay? So we can come up with a compound for this. It's a mixture of sodium and chlorine, or the elements sodium and chlorine. If I wanted to physically separate these from each other, I can't physically separate them. What I'm going to have to do is go through and chemically alter the structure of the sodium portion and chemically alter the structure of our chlorine, okay, to end up with the elements where we would end up with then sodium, which was our Na. I said I was going to write it out, and I didn't. And our chlorine. I think that's right. Orange is a bad color too, apparently. And our chlorine. So we could separate those into the individual pieces. So one of our primary assumptions when we went through and started to see these separations, when we could go through and do this, is that we can then break things into these smaller pieces. These smaller pieces, we initially said, were the smallest elements, or the smallest pieces of all matter. Okay? And then we could then do building blocks beyond this. Are elements the smallest building block of all matter? No. What are smaller than elements? Okay. Molecules are looking at a mixture, or sorry, not a mixture, a combination of elements. A molecule is actually, like sodium chloride, is classified as a molecule. Ultimately the same thing as a compound. So molecules don't work. What was the other one? Atoms. What's an individual atom? Let's say I give you an atom of sodium. Is that an element? Does the element specify an amount? No. So a single atom would be classified as an element. Okay, so we can't go to the atom. What makes up a single atom? There we go. So we get some subatomic particles. Okay, why do we call them subatomic? Because we thought that atoms were the smallest to begin with. And then we went, oh crap, our theory was bad. We had to go back and fix it. And that's where we got our subatomic particles. And we got protons, neutrons, electrons. So then we thought we were hot stuff and knew exactly what was going on until recently, in the last 100 years. It's actually probably 50 years. Are those the smallest particles? Nope. Okay? We can get even smaller particles than those. Thankfully, we won't talk about those. Okay? Beyond what we just did. Okay? That's getting into that hardcore physics/physical chemistry. Okay? So at this point, what we're going to be focusing on is that section on the far right. We're looking at our compounds and our elements and how those kind of interact with each other. Depending on where we get with the material, we'll probably talk a little bit more about heterogeneous and homogeneous mixtures as well. All right? Questions about any of those so far? I still got 5 minutes. I know that last 5 minutes felt like 10, but it was still only 5. Yeah?
Example of elements?
So elements, sodium, chlorine, anything on that periodic table on either side is an example of an element. Okay? And I'm going to regret saying that a little bit later. We do refer to things in their elemental state, and that can make things a little bit more complicated, but we'll discuss that when that shows up. But anything right now on either of these periodic tables by itself is considered an element. Okay? So now we got our periodic table. Okay, so this is where we're now going to start to address the things that you're going to have to start memorizing. Okay? So you want to check out Canvas, as we already listed out, elements for memory, and start to work on getting these things memorized. You'll notice if you take a look at your textbook, they go through and start to classify different sections of the periodic table according to some of the things we've already talked about. Okay, so we talked about different phases, solids, liquids, and gases, right? So where can we find those phases on a periodic table? And if you want to cheat, you can look at the two boards as opposed to what I've got up on the projectors. Anybody know where the solids are? Okay, why the black ones? Why do you think those? Anybody, let's try this. Does anybody know any element in black on the periodic table?
26 is iron.
26, Fe, we've got iron. Okay, what physical state is iron? Solid. Someone listed gold. Au, what physical state is gold? Solid. Both of those elements on our periodic tables here are in black, which means there might be some patterns showing up on our periodic tables. Maybe they're giving us some extra information. Okay? Turns out everything in black is a solid. Okay? Any other elements up there that are different from the black that you know? Okay, I need an element, not just gases.
Hydrogen.
Okay, oxygen. So if we look at the red ones, oxygen, what physical state is oxygen? It's a gas. How about nitrogen? Gas. Hydrogen? Gas. What do the red ones represent? Gases. Okay, so we got two main categories, both gases and solids. Are those the only colors up there? No. What else do we have? We've got the blue. Blue would likely represent, the only thing left over are liquids. How many different liquids do we have to be concerned about? Whoa, buttons. There are only two. We've got Br, which is bromine, and Hg, which is mercury. Okay? So we've got some classifications within our periodic table that allow us to come up with some of these patterns. We'll go through and look at further subcategories, our metals, nonmetals, and metalloids. Man, how many buttons have I pushed? On Monday. So we will finish up Chapter 3 and probably start moving into the actual calculations. I don't know. Still got 2 minutes. You got a question? Don't think like that. Yeah, well, that's wrong, so it's not going to work for you. Some elements will melt in your hands, some won't.
Is that smaller particle you're talking about that the spot?
That's one of them, yeah. So the one last thing I guess I could say here is I probably will test you on element names to see how you guys are doing with those. So you can expect probably periodically, and by periodically, maybe every day or every lecture, to be tested on a few different elements off of that list. All right. Again, they will probably primarily be used for attendance and also to see how well you're doing with your memorization process, so that by the time it shows up on the exam, you're like, this is easy. All right? Yes.
So do we have to, does the extra credit start this week? Like
Yes.
24 hours from today, right?
Yep. Extra credit is perfectly valid to do today.
Should we start editing or just?
As far as where to start,